There we go. Okay, thank you very much for that. And now some observations on philosophy. What have we done? We've done materials testing, creep testing, wide width testing, and for example, and I'll just pick up on this tensile strength. We do materials testing for tensile strength, and we get a value of T out. Okay, that could be from wide width strength, or it could be from isochronous load strain testing and interpretation. Okay, so now there's our materials testing. Now what about design? If we go over the page here, our design, whatever the design guide is, for example, US Federal Highways, for example, British Standard, for example, the Canadian Foundation Engineering Manual, which largely cites the US Federal Highways. Choose your design manual, your design guide, and you'll make an analysis, a geotechnical analysis, and the geotechnical analysis will tell you how much strength you require for the application. And at this point, we may be asking ourselves, is there a factor of safety in here? Okay. We're hunting. Where is there a factor of safety on the strength of the soil, for example? When I make my calculations to get T required. Whatever happens, there's my T required. And over here, I have the ultimate strength of the material from testing, okay? And it may be that the design guide imparts partial factors of safety. In fact, it will do. And that the T out, for example, from wide width testing, actually gets reduced to a T allowable. So now we got factors of safety on the geosynthetic. On the geosynthetic strength. Okay. And we've got a factor of safety on the soil. Or do we? Maybe we go hunting for it. And in fact, what we'll do is check carefully to see how and where factors of safety are coming into design, because this is where our confidence is coming. You know, we're providing for uncertainties. And in fact, philosophically, these partial factors of safety to consider different factors can allow us to see just how we're addressing explicit uncertainties. So when we get to the design, and it'll be more into the next lecture on embankments, thereafter on slopes, thereafter on walls, where we're invoking designs. And the Federal Highways is not the same as the British Standard. What we'll discover is that in design, you postulate. Okay, it's quite, this is probably the most important part of the lecture, quite frankly. In design, we postulate failure mechanisms. Okay? We postulate failure mechanisms. Failure mechanisms. Okay? That's the whole purpose of a good design document. It causes you to ask, how does the system behave? And how might the system fail? And of course, philosophically, what we're hoping is that when we look at these postulated failure mechanisms, we've postulated a number of candidate failure mechanisms, including that which is the, let's use the phrase, the path of least resistance, which is actually the way that it would fail if it could, all right? And so this comes down to people. People write design guides, and the experience and philosophy of the culture of the country tends to control the contents of the design guide and the way in which failure mechanisms are captured, okay? So these 2 pages are quite important as a roadmap as to how did I measure my strength? Did I apply partial factors of safety to it? What kind of design guide have I used? What kind of postulated failure mechanism? Am I comfortable that this has captured them correctly? And then ultimately, I want my T allowable, however I got it, I want the T allowable to be larger than T required, right? The T allowable must exceed the T required, okay? Let me just make sure I'm getting this nicely into the picture. Sorry about that, let me take this up a little bit. There we go, okay? That's how the system's working. This is the heart of geosynthetic design for soil stabilization, okay? And once we've got the strength, okay, and once we're convinced that we've got a satisfactory strength, then what about the following issue? Okay, so now let me continue with the thinking part here. Okay, fantastic. Here's my wall structure. Okay, and I've put in a whole bunch of reinforcement. And I've provided, let's put a base layer down there as well. They're all the same length. Let's make that the same. They're all the same vertical spacing, no problems. Okay, let's put in, they're all the same length. And even though it's not quite perfectly drawn, let's declare that they all have the same spacing vertically. Okay, and we have an allowable, let's count the number of layers, 1, 2, 3, 4, 5, 6, 7. And we have 7 layers at a T allowable, and that T allowable is greater than T required from design. Perfect, 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 perfect. That's basically reinforced soil in a nutshell. And it could be a wall, it could be a slope, it could be a wall on soft subgrade, it could be an embankment on soft subgrades, okay? All right, and by the way, continuing with the philosophy here, the writers of the design guides may say these design guides are good for these applications, and we provide you with equations, limit equilibrium approaches for applications like this, but the design guide is not appropriate for other examples or applications such as this, that, and the other, because we don't have a basis of codifying. There may be some constraints on just how universally applicable the design guides are, okay? Now, let me return to this image to say, so far so good. What have we left? What do you think? What do you think we need to do as a closing on design? Let's say we postulated a failure mechanism, and the failure mechanism is a locus of slip like this, okay? There's our postulated failure mechanism. Postulated locus of slip. Okay, let's hope we've got this correct. The final thing then to do is to make sure that we have adequate bonds. And for example, the bond will probably be most critical at the top layer here, because the confining stresses are relatively low, okay? So this is the strength part, right? Let's put this as strength, and this is bond. So now we need to know something about interface friction and or bearing if it's a grid. This is the strength aspect of the design, adequate strength, and now we need to know something about adequate bond, okay? So moving forward then, we flip the page, and let's ask ourselves a little bit about bond, okay? So I'm going now back into the literature. Let me grab a couple, bear with me, please. Here's a geotextile. Let me get another geotextile. Here's a black one, and let me get a geogrid. And I don't want you to think the whole world is made up of tensor grids. So here is a woven geogrid, and here's an ancient tensor grid, just because it's a little easier for me to show it to you in its full extent. Right? Now, can you imagine? I embed this in soil, and then I want to pull it out. Okay, let me turn it sideways. Okay, there's the geometry, and I want to pull it out. I want to know something about its resistance to pull out. I want to know something about its bond. And you might postulate a means by which you think that bond is mobilized. How does it mobilize the bond? Okay. Does this geogrid mobilize bond in a similar or an absolutely identical way to this geogrid? And again, let me translate it. Let me, can you imagine I've embedded it and I'm pulling it out, and it's being pulled past. Okay. And how does something that has apertures like this, or apertures like this, how does the interface strength get mobilized? And how does that compare to something that's a perfect sheet or fabric? Okay. And then I've got a woven one here, but maybe the best way to show the woven is to put it on a black background rather than the white background. And I brought in a, I don't know if that allows you to see it any better. It's a little bit of a magnifying glass. There's a small additional piece here, but I don't know if that weave, I'll move it in and out a little bit for you. I don't know if you see that weave or not, but can you imagine how soil is going to bond? How is it going to bond with a woven geotextile? How is the soil going to bond with a non-woven geotextile, which is a bit like Velcro, really, right? All these little, look at all those little fibers there. See where I can tease them out? See those? How does the soil bite into? How does it engage with that surface? How does it engage with a hard plastic? I don't know if you can hear it. Let me, right? How does it engage with that hard plastic? How does it engage with this coated plastic? I've actually got a strain gauge bonded to it here. Can you see that? There's a strain gauge that we bonded to it many years ago. But how does it engage with this? And then just to complete the thinking, the kind of how is this actually going to work? Tell me. What about, and I'm fishing around for a geomembrane. How about a smooth, very shiny geomembrane like this? How how does the soil engage or not with that surface? Or if I texture the surface, can you see that texture there? What does that textured surface do in terms of changing the interface friction? Do you think that if this was at the bottom of a heap leach pad with considerable normal stresses on the surface, do you think that the interface bond would be stress dependent? Let me throw another curveball in. Do you think the interface strength would be temperature dependent? Right? Can anyone tell me, please, what might be the temperature at the bottom of a municipal solid waste landfill? Can anyone offer a guess at a temperature at the base of North Vancouver's municipal solid waste landfill? Anybody want to throw out a number there? You're all very quiet all of a sudden. I'm not an expert on these things, but I was chatting with Jim Atwater, a retired colleague now, and he had been doing some field measurements, and the temperature was about 50 or 60 degrees centigrade. And can you imagine what that does to the surface hardness of this polymeric material? So, oh, we got a one in the chat. Oh, Terry Lynn, thank you. 40 degrees centigrade, not bad. And I'd say it's going to cycle, and I'm sure it cycles with the time of year. I'm sure it cycles with the activity that's going on the landfill. And the point, and thank you for the 40. The point is that that's a very different number to, let's call it, the liner of an Arctic, Northern Canada fuel containment spill at an airfield, where it might be down to negative values, and maybe you're building in winter as well. Okay, so what I want to do is to keep you thinking. Okay, I want to influence the way you think in this course. I'm not here to instruct you on everything that you can do for every possible permutation of design situations. I want you to think, and over the course of the next 10 to 11 weeks, I want you to ask the right questions. If you think and you ask the right questions, you will be a competent individual. And the greatest, I'll call it, compliment I could get from this course, if you're sitting in a design situation, you're out in field, you're asking the right questions, and someone turns to you and says, I like the way you think, okay? And then you can say, thank you, Dr. Fannin. I appreciate that, okay? So this is all about thinking, asking the right questions. Where do we go for information? Challenging constructively the way we believe the system works, okay? So having dealt now with the strength, let's move on to look at the bond, and I have a few thoughts to share with you on bond to influence the way you think, okay? Partly around this question of normal stress, partly around the question of temperature, okay? Now let me take you to this. It's actually an image from a PhD thesis at Cambridge University a number of years ago. It's direct shear box testing, right? There's actually, let me just show you. There's actually a very small offset. Do you see that very small offset there? And do you see the very small offset there? So this is direct shear testing. The top half of the box has been pushed over the bottom half of the box, displacing it just a little bit to the right. And markers that were embedded, and at that time X-rays taken of the markers, are showing the development of a shear band. Here's the shear band. That's where all the action is happening in the shear box. Okay. And a fellow, Richard Jewell, came along and he looked at, what if I orient the reinforcement? What if I orient the reinforcement in the shear box? I put some reinforcement in there and I see what that does to the increase in the shear resistance. And what he found was that at about an offset or a reinforcement orientation of about 30 degrees, he got the maximum increase. There was an optimal orientation of the reinforcement, okay? And that optimal orientation of the reinforcement, producing the maximum increase in resistance to shearing, was associated with orienting, let's say, one or more layers of reinforcement in the direction of principal tensile strain in the soil. And I think perhaps that becomes fairly self-evident to us. Now, if we take this recognition and I was to rotate this a little bit like that, can you imagine now, I'm going to draw on top of this, can you imagine now that I have, let me draw it as a slope. Here is a sloped structure. There is my ground surface. Can you imagine? Remember I drew that locus of slip earlier? We have a locus of slip. Right? Do you see that? I have a locus of slip. And it transpires that putting the reinforcement in horizontally is orienting the reinforcement across a locus of slip that is aligning the reinforcement in a direction that will cause it to go into tension in a reasonably optimal fashion, okay? That's how it works. Reinforcement is most effective when placed in the direction of maximum tensile or extension strain. And if it was a slope, or indeed, let me take it up and make it a vertical wall. It's this orientation of the locus of slip that's important to us, okay? And what that does, oops, I'm knocking things around a little bit. What that does for us is, let's now just examine one layer of reinforcement oriented at this reasonably efficient direction. And what it tends to do is generate tension, and it's done by deformation. The deformation of the soil bonded to the reinforcement takes it into tension. We have a component like this that we can, or so we have the tension here, which we can split into a vertical component and a horizontal component. The vertical component is tending to increase the normal stress a little bit. The horizontal component is tending to reduce the overall shear, okay? So that's a little bit of kind of the how does the system happen to work. And so now we have a keen interest in understanding this interface bond, soil geosynthetic interface bond. If I go back to the figure that we had a little earlier, see where I had the bond here, right? See where I had the bond. Let me just, there we go. So I can even use that same phrase, soil geosynthetic interface bond. Let me write that in, soil geosynthetic interface bond, okay? And perhaps we'll go in here and we'll put tensile strength. Okay. So how are we going to get this bond? I can, let me use, for simplicity, let me use a rigid sheet. I can get the interface bond by putting the rigid sheet in a test device, such as a direct shear, and shearing the top half filled with soil over the bottom half in which this is resting at the plane of shear, right? In other words, I could go in and go to the previous page. I guess I can do it here. I could get the interface bond by running a direct shear test, and I'm shearing over the surface. Let's take this out. I can get an interface bond in direct shear by shearing soil over the top surface of the material. And the alternative to direct sliding resistance would be to do a pull-out test. I could put the material in a box and then pull it out of the pull-out box. Okay, so let's look at bond in one of two ways. Let's look at bond in terms of direct shearing resistance or direct sliding resistance. Okay, so I have my shear box. I have soil in the top half. And I'm going to block off and put the material of interest, which will have to be a planar sheet. And now I can shear the top surface over the planar sheet. Okay. And I can get a shear strength that's a function of the normal stress and some coefficient acting into the angle of friction phi prime. Okay. And then I can look at the efficiency of that. Can you imagine if I was to get the value of that interface friction? Now let me look at putting in for this geosynthetic here. What if it was a geomembrane? Okay. And geomembrane. For example, PVC. For example, a very low density polyethylene. Or a high density polyethylene. What if it was steel? Just for purposes of comparison. Okay. And if I look at the, let me also go in here and do one other thing. Let me go in and put the normal stress. Okay. And what I can find is the efficiency. Let's look at data for a range of normal stress. Let me take the normal stress from 50 through to about 300 kPa. Okay. So there are data now. Let's go in and take a look at them. There are data from 50 through to about 300 kPa. There's our sigma n prime range. And what we find is that the interface strength, it's expressed here in terms of an efficiency, tan of the interface strength over tan of the soil strength. What percentage of the soil strength do we mobilize? And that will take us up to a fully efficient interface where tan delta is equal to tan phi. Okay, tan delta is equal to tan phi. Now let me, I've got some, here we go. So here's PVC, very flexible, right? Quite soft. If I was to take an awl or a screwdriver, I could push it in there and I'll indent the surface. That's in sharp contrast to the high density polyethylene, right? It's very hard, much softer, very hard. I will struggle to indent as easily in the HDPE as the PVC. So now let's look at contrasting the interface frictional strength, right? PVC, there is PVC, the triangles. Look, the inclination of the triangles, let's go in and do this in pencil. These are the data for the PVC, okay? And I don't quite fully mobilize the strength of the sand. I get a percentage of it, maybe 80%. As the normal stress goes up, as the soil is being further and further indented into the surface of the PVC by about 200, 250 kPa, I'm mobilizing the full strength of the sand. And how am I doing that? I'm doing that because, can you imagine? I'm going to see if can you imagine that the strength of the soil is indented into the surface of the PVC, and it's harder work for the soil to score itself like iceberg scour. It's harder it takes more energy for the grain, indented grain, to scour its way through the PVC. So it's kind of just essentially stuck with the PVC, and the grains of sand above it are moving. Really, you've forced the locus of slip back into the, in this case, the sand, okay? Contrast that with smooth HDPE. Okay, and the smooth HDPE has a much, it's less stress dependent, not quite flat, less stress dependent. The PVC is steeper and a much lower interface strength. In fact, it's lower. If I went in and put the missing circle here, which would be for steel. This is the steel. It's actually stress insensitive. But do you see that HDPE has a lower interface strength than steel, for example? Okay, so there's an appreciation. And you know what we should do as well is to go in here and put a certain temperature. These data were acquired at UBC, and it was in the grad soils lab many years ago, and the temperature is about 20 degrees centigrade or something like that. Okay. That's our first shot at bond. What do we take out of it? Oh, by the way, if we were testing a geotextile, we would get almost a full interface strength. And can you imagine, let me again go back to my geotextiles. Can you imagine the manner in which the sand, if it's sand, will embed in the weave of the woven geotextile? Can you imagine the way in which the sand will embed itself in the Velcro-like surface of the needle punch nonwoven. Now, that's fine, but it's not going to give us, and we might well be interested in the interface shearing across the surface of a grid, in which case we know this, we know the interface strength of the material in direct shear, and we know what percentage of the area is available, and we get a composite shearing of soil over the plastic and soil over the soil in the aperture. So we can get to that. But what about interface bond in pullout? Okay, so let me sketch a little pullout test device for you. Okay, I'm going to fill it with soil, and then we're going to pull the geosynthetic out. Okay, this is the embedded length, and we'll pull it out by clamping on this end and pulling it. And if the geosynthetic is a sheet, well then it's fairly self-evident. Sorry about that. I just got a little carried away in putting the presentation there. So if it's a sheet, the interface shear, sigma n, there's our tan delta prime, and the pull-out resistance is 2 times the top and bottom surface, the embedded length times the width times the shear strength on it. Okay. If I was to draw it in 2D, I could put the length in. Let's do the length here, just so we can see it. There's the length. And it will have a finite width, or I could have the pull-out force per unit width if I divide through by the W. Okay. Now, if it was a grid, let's consider a grid, a geogrid. So the sheet might be a geotextile, the grid a geogrid. Now we have an interesting, we don't have tan delta, which is a function of phi dash. We've got a bond coefficient. And this bond coefficient is picking up the fact, okay, let's get ourselves sorted here. This bond coefficient has an element, this is the bond of pulling out the grid. It will have a component which is shearing over the surface that is solid, and it'll have a component because there'll be an element of bearing. Can you imagine? Here, let's consider my pinky finger is just a grain or a gravel piece or something, but can you imagine the interbeddedness, and we get a bearing action. We get a bearing action as this is being pulled out. So we have 2 components. We have a shear component and a bearing component in pull-out. A shear component and a bearing component. Okay. The shear component we can get knowing the interface shear strength. If we wanted to look at it from fundamental principles, the bearing component, aside from, let me go in and work through some of the parameters here. A sub S is the percentage area that's solid. Let me just see, do I have this little page? No. So alpha S, solid area, percentage. Alpha B, bearing area as a percentage of what's being pulled out. let's not get too much into the details because it's only ever going to be reported as a kind of a single number, but this is the constituent pieces. Big B and big S. Let me illustrate that with regard to this. This is the thickness B of the bearing element that's being pulled through, and S is the spacing. Got to come out a little bit further again. S is the spacing between the bearing elements from here to here. Okay, so let me try and capture that in a sketch. There's one bearing element, there's another bearing element, that's what's making up the grid. And S is the spacing between the bearing elements, and B is the thickness of the bearing element. Now, my reason for bringing this to your attention is to recognize that the bond coefficient is driven by geometry, interface friction of the surface area, and thus the bond coefficient for this grid, with its hard plastic and its spacing like this, that bond coefficient will be different to the bond coefficient, for example, for this grid, with its geometry, spacing, and surface treatment of the woven materials. So the bond coefficient is going to be product specific, just as you saw that the interface shearing resistance or direct sliding resistance is also product PVC versus HDPE specific. And it's going to be controlled by the strength of the soil in the background, given phi dash as well. Now we've covered off everything in here except for this stress ratio. And Richard Jewell, I put this in, it's probably a bit redundant, but the stress ratio, just to complete things, there was an attempt in the early days. Interestingly enough, I've seen this figure in US federal highways ancillary design support documents, but the bearing ratio is also a function of the angle of friction. Okay, so really we could go into this bond coefficient here and argue that this component is also a function of this. Okay, so that's what I'd like to say about bond. And why were we talking about bond, either in pull-out or in direct sliding resistance? And the reason we were talking about bond was, if I went back just a little further, we need to provide in design for adequate anchorage length. Thus, we need a bond coefficient, because in design we get the length of the reinforcement in a number of ways, one of which is to postulate the locus of slip, and then to add an adequate bond length, taking into consider factors of safety to get the overall length of the reinforcement for an internal stability analysis. Okay. The last 2 pages, and this is a recasting of this concept in US federal highways language. So I want to close things off. We won't go through all of this in detail. The first US federal highways design document was written in 1990 by Barry Christopher and a bunch of other people under contract to US federal highways. And they looked at the pull-out resistance. It's exactly what we're looking at here, this pull-out resistance P. And they looked at the pull-out resistance and they captured it in a slightly different way. There's the normal stress, there's the strength. Here's the constant, which for a sheet is 2. We would find that. That's written in here. But the key thing that I wanted to get out of it is US Federal Highways casts the bond coefficient as, it's a curious phrase, F star alpha. That is their bond coefficient in North American design practice. And I give you this page and the page over, but please don't, get caught up in the details or anything like that. But if we take this bond coefficient down to here, the F star part of it has 2 components: passive resistance and frictional resistance. This is bearing, and this is sliding. Okay, so it's the same thing. And I wanted to close by looking at a design guide or the design terminology. That's a better way of putting it. And you'll see all sorts of ways of trying to capture it and word it here. But the bottom line is that the F star has 2 components, sliding and bearing, and it's a bond coefficient. It just is not exactly the most intuitive way of describing it. Okay, and that's really the scale. The alpha is I won't even go into the details. It's gonna dive us into more detail than we need now. We'll come back and look at this a little bit in the lecture on design of walls and US Federal Highways approach to that. Okay, so there we go. Interim summary. Let's have a little human connection here, people. That's pretty much the end of the material properties and its treatment. Strength tests, creep phenomena, soil geosynthetic interface shear strength. The durability I'm going to park for a separate lecture of its own. Okay. How strong is it? Is it subject to creep? If so, how are we going to account for that in strength? And then what about this soil geosynthetic interface shear strength, indirect sliding and bond? Now, once again, let me just ask: do you guys have any big picture questions? Any little detailed questions? If so, please either unmute yourself or let me just take a look in the chat box here. If you've got any questions, I'd be delighted to handle them. And as you may be choosing to formulate a question, let me tuck away the material properties and move into the principles of analysis and design. Okay. And once again, please let me reinforce: think and ask the right questions. So I'm going to open this up again with the thinking part, because really the trick in being a competent designer, in this case with geosynthetics, is all about asking, how is this system going to perform? And how are we going to capture that behavior? Okay. Now, we'll look at bearing capacity, mostly with regard to vehicle loading of thin gravel layers. Oh, just a second, there's a question in the chat box. Ryan, how about geosynthetic, yes, e.g. geotextile sliding on an HDPE. Let me find my HDPE. There it is, 60 mil HDPE. And let me get contrasting geotextile. Here it is. That interface strength is going to be very low. And you know, let's take it up and look at it. In that interface strength will be very low, geotextile to HDP geomembrane. And let me get another, here we'll clear the decks just to, let me get another geosynthetic, another candidate that could go on top of a geomembrane, and that would be a geonet. You see the geonet as a drainage medium. And man, this is going to be super slippy. This is probably going to be 6 or 8 degrees interface friction once we get some normal stress on it, okay? And thus, yes, you could have geosynthetic to geosynthetic interface, particularly in waste containment facilities, where we may have a geomembrane with a geonet, and then I'll put in a non-woven geotextile. Let me get a contrasting color. Let's put in a gray one. We may have 2 or indeed sometimes 3 interfaces all at play. And in fact, when we go to look at the Kettleman Hills landfill case study, a little later in the course, we'll discover discerning which is the weakest, and then forensically, if you had a slip, going in and trying to forensically find evidence for that will be quite testing. But we could have interface slip zones that are as certainly less than 10 degrees, delta maybe about 6 or 8 degrees in terms of interface friction. And the way in which you would test it for that composite would be to do some direct shear testing. Once again, Ryan, it would be a matter of just setting it up, and that's what was done forensically after that Kettleman Hills failure. It's about nearly 30 years ago now. Okay.
Dr. Fanning, can I ask a question?
Yeah, far away.
I had a question on the framework for analysis and design, specifically the step between T ultimate and T allowable. I know there's in the flow chart, there's a step for partial factors of safety.
Yes.
I'm just wondering, because to get from T allowable to T required, those are based off design codes. So from T ultimate to T allowable, that partial factor of safety, is that just based off of engineering judgment?
No, it's not actually. The reduction from T ult to T allowable with, let me see if I can annotate it here, US federal highways will take T ult from the wide width test. And in the design guide, let's put wide width. And in the design guide, for example, on embankments or on retaining walls, will suggest partial factors of safety. So in other words, the design guide will take you from T ult to T allowable. And in the British standard, it's unfortunate that the acronym is BS, but it's BS 8006, which will be from isochronous curves. And BS 8006 will also apply, it applies different. I mean, the US federal highways will have 1, 2, 3, but 4. They've got reduction factors and then factors of safety, and we'll see the subtleties of the difference. But let's say there's a package. Let's call it a series of, and I'm going to put RF because we'll see that when we get to design. These are reduction factors, a series of reduction factors and a factor of safety. Okay, and the British standard likewise has a series of, and they call them partial factors of safety. and they call theirs FM. And there's FM11, FM12, FM21, FM22. It begins to get into, it feels like structural design because you're putting all these partial factors for different things. And that's in the design guide for the geosynthetic, along with potentially additional factors of safety on the soil to get the T required. Does that answer your question, Jason?
Yes, and just one quick follow-up question on that. So
Absolutely.
For the T ultimate from the wide width test, is that, so that's the minimum average roll value, not the typical value, correct?
Correct.
So there's already a statistical factor of safety applied to the T ultimate.
That's absolutely correct.
Okay.
Yes. And philosophically, I could chip in one other observation here. That's why geosynthetic reinforced soil structures tend to behave quite well in seismic zones, because by the time you've factored down from T ult to T allowable, and your T ult is a statistically low value for the production line, you are using a very, very small percentage of the strength of the geosynthetic with the T ult. And it's really where these two crosstalk, because using a very small percentage of T ult as T allowable means that you're loading it so lightly, it's not going to creep that much, number one. And number two, you have a tremendous reserve of strength between T allowable and T ultimate, that if you come along and you just put a very transient demand on the structure, like an earthquake, the geosynthetic says, where's the effect of, go ahead, make my day, because I have got so much untapped strength that I'm not using so that I don't creep, that you can come along and put your short-term demand on me. I can accept it without breaking intention. And it's such a short duration demand, I won't creep much in the 2 minutes of the earthquake. So that's kind of a philosophical complement to your correct observation on T ult being the statistically low minimum average roll value.
Okay, thank you.
You're welcome. Any other questions? Okay.
Like reduction factors like NALEX provides reduction factors, and I thought those were the only reduction factors. Then you use the design methodology to, I guess, US. So what are those provided by NALEX when they give a couple of reduction factors to?
Yes. So I'm going to speculate. Let me pull up the big picture here. NILEX is a supplier or a distributor. So let's acknowledge that in the background, let me sketch this. There's the manufacturer. They produce the geosynthetic. And then they get it to the construction site through a supplier or distributor. Let's call them a distributor. Okay. Their distributor, then I just want to check spelling here, people. Bear with me. I think it should be distributor with an O. There we go. They work through their distributors. And the manufacturers will provide a technical data sheet. They have a data sheet on their product. It will give the minimum average roll value, the wide width strength, the grab strength, et cetera, et cetera, et cetera. Let me just get back to my Zoom so I can make sure you can see this. So the manufacturer has a data sheet, and they supply the data sheet to the distributor. You can actually go online and look at those data sheets. The distributor should really just be relaying the material properties to you that they obtain from the manufacturer. The distributor's role strictly is not to provide factors of safety, nor is it really the manufacturer's job to provide factors of safety. They should give you the strength data, and then you apply factors of safety either in strict accordance with design guidance, or you may choose to even enhance them, because many of these factors of safety are suggested minimum values, okay? And so I'm going to speculate that if NILEX as a distributor are speaking to strength values and commenting on appropriate factors of safety or partial factors of safety, it's going to be that the manufacturer is drawing those from certain design guidance and simply relaying them. But what you want to do is either directly online or via the distributor, just get the technical data sheet and then work with them. Any other questions? Okay, so let's draw a line then under the material properties, and let's move forward to the resource access roads. And I believe you should have, I think I released these notes to you. I'm going to speak to them for about probably 25 minutes. I want to reserve a little bit of time. I want to reserve a little bit of time at the end of the lecture to speak to an assignment I'm going to give you and the expectations for that assignment and how the assignment ties into both the material we covered last week and today, and then looking forward how it informs our approach to embankment design. Okay, so let us see how far we cover. And my main intent in this opening portion of the lecture is to start again with thinking. Okay, so this is not a flow of directives. This is you know, what do you think? What do you think? So philosophically, let's look at this. It's actually a series of sketches that were made by a very good friend of mine, Enio Palmeira, at the University of Brasilia. We shared an office together. He was a PhD student, I was a PhD student at the time. Now, let's look at the embankment. Do you see this sketch for the embankment here? There's a really nice series of thoughts, right? Here's the embankment on soft ground, right? And this is a layer of geosynthetic reinforcement at the base of the embankment. Here is a steep slope. With layers of geosynthetic reinforcement in it. Okay, and then the one that we're going to actually look at is this one. We'll get to it. We're actually going to get to it third in the sequence of thinking. Here is, let's argue, a resource access road. Perhaps this is part of a vehicle loading. We have a ballast layer or running course, and we may or may not have a geosynthetic layer separating the running or ballast layer from softer subsoil. Now think of this, and I'm going to start with the slope. It's on competent ground. It's on a competent, firm foundation. Okay. You build it, and as you build it, you invoke tension in the reinforcement. there is the reinforcement force that's required. And in principle, at the end of construction, all of these little arrows are at the end of construction. Let me go through and capture all of them. Okay. End of construction. The force in any layer of reinforcement in the steep slope gets mobilized, and it remains constant pretty much for the service life of the structure. If it was public works and it was in the United Kingdom, the service life of the structure is 120 years. Okay. Let's go to the embankment. Okay, so let's go from the steep slope to the embankment. And let's look what happens. As we build the embankment, the force and the reinforcement is going up, but it doesn't remain constant. The force and the reinforcement goes down with time. Why? Why does it do that? Why does this do this, but this does that? Why is that? Why do you think that is? Do you have any thoughts? Does anyone have any thoughts as to why this system behavior is different? Right? And it's a system. Any thoughts on that? Does anyone want to throw out an idea?
Is it active versus passive loading?
Active versus passive. Do you want to explore that a little bit more? Anyone else want to chip in? You're onto something, I think. And let's ask ourselves, where is the capacity of this system coming from? Where is the capacity of this system coming from? And do any of those capacities change with time? Right? So it's a little related to what you're hinting at. Any thoughts? And if not, I'll cut to the chase. But
would it be consolidation of the soft soil?
Absolutely, absolutely. Thank you, Daniel. This embankment on soft soil, the soil, let's call this a soft foundation. If the soft foundation consolidates and if its strength increases with time, then the capacity of the system is increasing with time. If the demand on the system, the height of the embankment, remains unchanged, then as the strength of the foundation soil contributing, for example, to the stability with a locus of slip, right? If the capacity of one component in the system is changing, then the required strength of the reinforcement, the demand on the reinforcement is diminishing with time. Were this not a competent foundation, but a soft foundation, and it's a tricky design situation when you're building retaining walls on soft foundations, design guidance tends to start out throwing caveats in left, right, and center. But if it's a competent foundation, there's no change in the capacity of the system. Whatever is your demand on the reinforcement, the day after the end of construction, it's going to stay like that. And that's why creep creep is a big concern now. We don't really have much concern for creep, if in fact the load is being shed off the geosynthetic, right? So now what we're doing is we're thinking. We're asking ourselves, how does the system behave? Because you may not necessarily find the perfect design guidance for every application, and sometimes you're pushing things a little bit. So the key question is, how is the system behaving? Okay, and that takes us to the unpaved road over here, where the demand is a bit more cyclical. We may not have that much capacity enhancement from consolidation of the subgrade. We may or may not see a little bit there. You could question that, but largely it's a transient demand driven by the nature and axle loading and things like that. Okay, I put this to you so that we can begin to see how, for bearing capacity, which we have here, the principles of analysis and design and bearing capacity, oops, can you see that? They may differ to the principles of analysis and design for embankments on soft ground, which is what we see here, and what we see here, which may differ from the principles of analysis and design for reinforced soil slopes and retaining walls and bridge abutments, for example. Okay, so I want to continue this influencing the way you think, and it'll cause you to ask the right questions and grow your competency. So, how does the system work? So I'm going to take you to what I think is a very nice piece of work by a guy called Richard Jewell. And there's just one idea, okay? Interesting idea. Now, Richard worked for a company called Binney and Partners. Then he went and did a PhD at Cambridge University. I think he'd done his undergraduate at Cambridge as well. I first met him when he was an industrial fellow, sponsored by the UK Engineering Society, and he was an industrial fellow at the university where I was doing my PhD. And he subsequently wrote this book. It's actually a very good book, 1996. I think the library has a copy of it. And it was a book funded through the Construction Industry Research and Information Association, Syria. They actually write some pretty interesting stuff, okay? And he looked at, how is the system working? How is this bearing capacity theory? How does it apply to my unpaved road scenario and various, you know, similar setups? And so I'm going to spend about 10 minutes just working through the theory, and wherever I get in the next 10 minutes, then we'll call this lecture on to a halt. I'll have to pick it up next week. That's no big deal. Because I want to make some comments about the discussion exercise that I'm handing out today. But here's the key insight, okay? He's looking at bearing capacity. And there may or may not be a water table present in the soil. And he asks, what is the bearing capacity of a footing, where the footing may have a vertical load or it may have an inclined load, and the inclined load may be centrally applied or eccentric from the center line of an infinitely long footing. And he starts there to ask why is it that the geosynthetic might improve the bearing capacity? Okay, and I'm going to let me put this question quite carefully. In fact, does the geosynthetic improve the bearing capacity, or does the geosynthetic stop the bearing capacity degrading as it would otherwise do? Okay, so classic soil mechanic problem. I won't dwell on the details, and you can certainly read the text. Let me walk you through the highlights. He goes through and constructs an expression for the maximum bearing stress. If it's a cohesionless foundation, it has two components. It has the component from the energy required regarding the self-weight that's displaced in bearing. And if the footing is embedded below the ground surface, it has a component due to surcharge loading. If the load is inclined, there'll be inclination factors. And if it's offset from the center line eccentrically, then there'll be a reduced foundation width. That's what's in there, and you can read it through. And then he goes through and says, all right, let me account for the groundwater level as we would ordinarily do. That's a housekeeping item. Okay. And then let me come along and get these inclination factors for substitution into the equation. And it's the question of the influence of inclined loading. And his argument, I think, is neatly done. He says, you know, what does inclined loading do to bearing capacity? Let me, okay. What does inclined loading do to the, and I'm going to, let's invoke this maximum bearing stress, the maximum bearing stress. Okay, what does inclined loading do to the maximum bearing stress? And we'll go looking for the answer now, okay? So he invokes Vesage. You can go to various bearing capacity factors, and he calculates the values for the inclination factors, right? For the reduction factors for load inclination. And there's our hint, the reduction factors. Question, what does inclined loading do to the bearing stress? It reduces it. How much does it reduce it by? So he goes through and crunches the numbers. If the load inclination is 0, no load inclination, then we have the full bearing capacity factor. Inclining the load with load inclination, we degrade or reduce load inclination reduces the bearing capacity. Okay, that's the answer to the question. If the question is, what does inclined loading do? It reduces the bearing capacity, and quite significantly. Okay, as he observes, a load inclination of about 10 degrees will reduce the bearing capacity to about 50%. It's quite punishing. And what happens is that inclining the load produces an outward acting shear on the surface, because it's got two components, a vertical and a horizontal component. And that outward acting shear degrades the bearing capacity. Okay. And this diagram applies for all angles of friction. Okay. And this is another representation of it. There's the full bearing capacity, a load inclination of 5 degrees, a load inclination of 10 degrees, a load inclination of 15 degrees, and there is the reduction. It's the same thing, it's just now expressed in terms of the bearing capacity factor. Okay. This we don't need, that's redundant. And he looks at it from an undrained bearing capacity approach. He looks at the undrained bearing capacity. Let me just make sure I can capture. Yeah. For the drained bearing capacity. The important point in figure 519 is that load inclination of only about 10 degrees is sufficient to half the capacity of the foundation. Okay. And that's a drained analysis. What about an undrained analysis? So he does the same thing. He looks at the undrained bearing capacity. He invokes work of Malcolm Bolton at Cambridge University. And in fact, Malcolm Bolton was a fellow student at Cambridge at the same time. Here is Bolton's equation for that. And if you crunch through the numbers, here's the, right? In the absence of its outward acting shear stress, right? That's a case of when alpha equals 0, but it gets reduced to half that value when the maximum shear stress, that's an outward acting shear stress. If you take the time to read through, and I don't want to be a talking Syria report, but if you read through, there's the magic phrase, half the value, and approximately 50% reduction. And that's the undrained analysis. So irrespective of a drained or an undrained bearing capacity calculation, the presence of outward acting shear stress underneath the footing will reduce the bearing capacity. Okay. And what the geosynthetic does when it's present in the system is to take up that outward acting shear stress. So I'm going to illustrate this in this figure, and then we'll stop in this thinking portion, and I'll move from the lecture to the discussion exercise. Here is a schematic representation. It's actually from model testing. This would be the characterization of the vehicle loading. So it's really a symmetrical or almost symmetrical double footing analysis. This is an unreinforced system. Here, let me put this in. Unreinforced. and below it is a reinforced system. And it is reinforced with the presence of a geosynthetic at the interface between the soft soil and the dual footing arrangement. The same combination, let me see if I can take this out a little bit further. That's one pair. The subgrade has a certain strength. Here is another pair below, okay? So we have the unreinforced system here, unreinforced, okay, and the reinforced. And again, the reinforced has an element of, that's the geosynthetic there. And in the experiments, by digitizing markers that were being displaced, you see the displacement vectors here. So by moving from the displacement vectors, let's look at the upper one as the pair. There are displacement vectors. And what happens in the unreinforced system, as Jewel argues it, I think convincingly, is these lateral deformations here, 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 and here, these lateral deformations degrade. They are these lateral deformations on the surface of the subgrade degrade the bearing capacity, and the bearing capacity reduces. By putting in something, in this case, the something is a geosynthetic, by putting in something that can go into tension, you have less outward acting shear stresses. Okay, so by inhibiting the action, you're in essence promoting more of a vertical. Let's say here's the vertical. You're promoting more of a vertical. We've actually got, strictly we've got to take this down to a virtual footing that's here. So you're promoting less inclination of the bearing capacity of the gravel on the subgrade. And here, again, we need to project it down to get the virtual footing. Here you have greater outward acting shear stresses. Thus, both systems are degrading in their bearing capacity compared to the theoretical maximum. Now this is the key, I would call it the key insight. I'm just looking for a page in my notes, and where is that? Yes. So the thesis of the argument is, in the ideal world, you would have 100% of the bearing capacity. It will degrade with the equivalent inclination of the loading at the contact with the subgrade. The degradation in the unreinforced system is much greater, relatively speaking, than the degradation in the reinforced system. And thus, by incorporating a layer of geosynthetic reinforcement in the system, bear with me, thank you very much. sorry about this, there we go. By incorporating a layer of geosynthetic in here, you are acting to inhibit the degradation that would otherwise occur from the theoretical maximum bearing capacity associated with the outward acting shear stresses on the surface of the soft subgrade. Okay, and we'll draw a line at this point. I'll give a little human touch to it here. We'll draw a line under it at this point. I will return to look at a case study, because this begs the question that a stiffer and stronger, let's ask the next question. Okay, is it correct? Here's the hypothesis. Hypothesis. Okay. A stiffer and stronger, but especially the stiffness, geosynthetic should yield a greater improvement. So if that's the case, let's run a field trial and test the hypothesis that a stiffer and stronger geosynthetic will be more efficient at taking up those outward acting shear stresses, and that the greater the stiffness of the reinforcement, the greater will be the maintenance of bearing capacity. Different stiffnesses. Can you imagine that you're now saying, hey, the stiffer the reinforcement, the less degradation there should be. Okay, so let me park those thoughts of Richard Jewell, very nicely captured on soil reinforcement with geotextiles in this construction industry serial report. And when we return next week to pick up the lecture material, we'll look at a full-scale field trial, and let's see if we capture evidence of this phenomenon. Can we test the hypothesis and find it true or false? Okay. Now, I released some materials, and I'd like to speak to them. Okay. So now what I'm going to do is we're going to say, okay, oops, don't go away on me. I was going to do a timeout on the lecture. Now let's turn to learning objectives of the course and material to complement it, okay? So we're in here, we're in lecture number 2, no big deal, we can follow the material. But I want to release this discussion exercise, okay? And you might say, gee, what's a discussion exercise? What's going on here? So let me speak to the discussion exercise. And I've released 2 pieces. I'm going to release a little bit more. The discussion exercise. John Busbridge and a series of co-authors wrote a report. They wrote this report, which I'll release to you, prepared for Transport Canada, written by John Busbridge at Golder Associates and collaborators at the University of Laval, August 1985. Some time ago. It's actually a very interesting report. So I'm going to give it to you, and the authors come up with a number of conclusions. Let's take a look at conclusions 3, 6, 7, and 9. Okay. So you could go to the report. I'm going to release the report shortly, as in after the lecture, and you can go to the conclusions. Conclusion 3, for example. And here is a conclusion. Remember, this is the report that has isochronous load strain curves in it, for example. Now, for each of the conclusions in the report, I ask you to report the evidence presented in support of the claim, list the strengths and weaknesses of the evidence, and comment on whether, in your opinion, the evidence presented is sufficient to warrant the conclusion. So you're going to use some judgment, okay? You're going to use some judgment on this. And to guide your investment of time and effort in reading the report and reviewing the conclusions, I provide you with two additional one-pagers, okay? The first one-pager is a grading rubric. I think I've released this. I haven't released the report, I'll release it, but here's a grading rubric, okay? And the grading rubric speaks to your written communications, the logical flow of what you write, the manner in which you treat the supporting evidence, and your evaluation of the analysis and claims made by the authors of the report, okay? And the grading rubric has a series of guiding expectations that will declare your submission as exemplary, or perhaps skilled, or perhaps competent, or perhaps basic. And I'm sure none of you are going to end up in this horrible bin on the right-hand side here, unacceptable. Okay, were I to go in, I'd say, you know what, if you're up here, you're in the 90%. If you're in here, you're in the 80%. Here, you're in the 70%. Here, you're in the 60%. And here you are less than 60%. And that's not a passing grade in a grad course, okay? So there's a grading rubric that might give you a sense of where the goalposts are in this learning objectives and its evaluation. And the second one-page guiding note is the following. And I produced this a number of years ago because what I found is that people were summarizing the report. Instead of reporting the evidence, listing the strengths and weaknesses, and commenting on whether it's sufficient to warrant the conclusion, all I was getting, excuse me, sorry about that, all I was getting was a summary of the report. And so I write here, listen, what are the discussion exercises, and there'll be three. This one's on embankments, the next one will be on walls, and the third one's on barrier systems. And I say, listen, this is what this is what ideally should be happening, right? Ideally, the authors would present data, qualitative, quantitative. They'd analyze the data, they'd discuss the analysis, and they'd present conclusions that follow logically from the analysis and the discussion. That's the perfect world. Now, we don't live in the perfect world, but that's the perfect world. For those of you that go on to do an MASC or a PhD thesis, that's the standard ultimately you'd be holding yourself to. So thus, the conclusions would be evidence-based, and the claims would involve little or no speculation. That's the perfect report, okay? So now I ask you to go in and please don't summarize the contents. Please don't submit a summary of the report, right? Rather, this is what I ask you to do, okay? Read the report, right? Report the evidence. Do it in a brief and succinct manner. Then you're asked to list the strengths and weaknesses. So please list them. And then finally, you need to say yes, no, or maybe you find the claim warranted by the evidence that the authors present. Alternatively, you might say, no, I find the author's claim to be rather speculative, and here's my justification for that claim, okay? And once again, there's the kind of the guiding rubric which I will release. Now, what do you do with this, okay? The deliverable. In advance of next week's class, submit a soft copy to me by email, okay? And then bring to class with you, or have available to you, a hard copy of what you submitted, because you can annotate it and mark it up with additional observations and comments, okay? That's for the discussion exercise. How does the discussion exercise fit into the course in the big picture? The evaluation in the course comprises 3 discussion exercises. The first one worth 5%, and the next 2 at 10%, along with the design assignments, right? For which a grading rubric will be provided. So I'm going to release the grading rubric, okay? The first one's worth 5% because I think it's going to take a little calibration to the expectations of the discussion exercises. So once again, let me turn to you. I'm mindful of time. We're really close, actually. Apologies about that. But are there any questions? Any questions whatsoever on the discussion exercise, its intent, the deliverable of a soft copy to me in advance of the lecture next week, because in the discussion exercise we'll set aside, or in the lecture we'll set aside some time to go through and look at the solutions to this problem. Any questions? I'm checking chat. I'm checking for anyone that wants to ask any questions. Okay, either I've made it entirely clear, which would be brilliant, or else you just need to let the dust settle and read through the kind of the rules of engagement, and I get that. So philosophically, when you're in practice and philosophically you're reading design guidance and you're maybe reading the odd case study, the question is, hey, has what's been written, is it worthy enough to influence the way I think? And the purpose of this discussion exercise is to look at this. It's a brilliant case study. A tremendous effort, made in Canada case study, and to ask yourself, how many of these conclusions are going to influence the way I think? And informed by that, when we start looking at embankment design on soft ground, you will be coming at it from a very informed manner, because you will have read a report on the effect of geogrid reinforcement on the stability of embankments. There's actually 3 on a soft, sensitive Champlain Quay deposit. Okay, and these authors are a bunch of very, very, very good people. John Busbridge, Victor Milligan. I'll tell you a few stories about these guys next week. Pierre La Rochelle. I have a John Busbridge story, I have a Victor Milligan story, and I have a Pierre La Rochelle story. They're all absolutely fantastic people. Anne Poshman. It's a Oscar-winning series of authors on the report. Okay, so thank you. I realize I'm a minute over my time. Apologies for that. I will endeavor to discipline myself a little bit more. Thank you for bearing with me. I'll hang around for a few minutes after the lecture. If anyone wants to chit-chat, feel free to linger too. And otherwise, for those of you that are dashing off to other things, I wish you a good day if you're in Canada. I wish you a good night's sleep if you're in Tehran. And Emmanuel, yeah, it's you must be getting close to early morning there. I'm not too sure. You'll have to help me out on that one. Anyway, to all of you, I wish you an excellent
evening.
Yeah. What time is it with you, Emmanuel?
It's 8:02.
6:02.
2 minutes past 8.
2 minutes past 8.
8:02.
Okay, thank you.
Yes.
Yeah, bright and early in the morning. Anyway, for anyone that
No,
wants to...
PM.
Oh, PM.
Yes.
Oh, yeah, you're just ahead of Europe a little bit. That's right. Yeah.
Yes.
Excellent. Okay, so thank you very much, people. Please, I'll hang around if there's any chit chat to be had. Otherwise, feel at liberty to slip away and get on with the rest of what needs to be done for you today. Take care.
Thank you.
Thank you.
You're more than welcome. More than welcome.
Thanks.
Thank you.
Thank you.
Yeah, and most welcome.